what I would say is that this component, isn't that an upstream component?
Yes.
Isn't downstream positive? I need everybody to pay attention. Isn't this component upstream? Isn't downstream positive? So therefore, by that convention, I have to make that a negative number. So I'm going to go 1.855. So this is the current going downstream. That makes it positive because downstream is positive. This is the component there, which is now upstream. Okay? So what does that mean? This boat is actually not going to go downstream. It's actually going to go upstream. They overcompensated for the current, didn't they? Okay? So now I think we're all set. We can find the time with this, put the time across, and calculate this. Okay? So the time is going to be this divided by this. So 40.23. Oh, 4.3. Right? Okay. What's the net result of 1.2 downstream and 1.6 or 1.855? Yeah, 0.655, right? So that's going to be negative 0.655, which means we're going upstream, right? Is what that is. So this times that, so times is negative 26.5. So in the weirdest way, it's negative 26.5 meters downstream, which means it's upstream, yeah? So our questions are, what time does it take to cross? Why does it take a longer time to cross? Yeah, we're going also upstream, and so some of the velocity is in a different direction than across. The shortest way to cross is to point straight across, but you get washed downstream. Otherwise, you're going to waste some of your velocity counteracting the current, right? So it takes longer, right? Where does it land? Well, it's actually this one we overcompensated, so we went upstream. Actually, 26.5 meters. That's why that's negative, because it's negative downstream, right? And then velocity is seen from above. I'm not going to do the whole thing, but this is the picture of it. It's over 2.968, and then upstream 0.655, right? Say it again. No, we're good. Okay. So that's that one, right? Is we could do that, right? And we could find the angle and the hypotenuse, but I don't want to do that. I'd rather do dun 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 dun. Okay. Now we want to go straight across, right? So we're going to do that crazy thing, and this is what I would do, when I was canoeing, is I would have a calculator in the bottom of the boat, and I'd be sitting there hitting the keys with my toes, and I had a compass on the bottom, and I'd be like choosing, this is how I calculate that perfect angle. Either that or I just sort of guess and adjust the speed and angle of the canoe so that I went straight across. Okay? So final one is that we're going to go straight across at some perfect angle. Now I'm going to start with this. Across and downstream. Across and downstream. What do we know? If we point at some angle up there, what do we know? Yeah, 1.2 is going to be one of these guys, right? And we know that there's going to be, since we're pointing at some angle, we're not straight across, right? That there's going to be some component. And what are they going to add up to? Yeah, these guys are going to add to 0. Because why? Because our displacement is going to be, if we go straight across, this guy's going to be 0, right? Downstream, we're going to be displaced 0 because that means that we go straight across. Why is it called a ferry, a downstream ferry? Is it because in the old days, ferry boats actually did that to cross rivers? Ferries as in like Boone's and Taylor's and Canby. Before Canby was replaced with like a little machine that carries you across, it was an actual boat. You got on the boat and the ferry operator pointed upstream and used the speed of the motor to keep you from getting swept downstream, right? So this displacement is 0 because that's where the road is, yeah? It goes straight across. Yeah?
Wouldn't the other S be 120?
Yeah, this S is 120, right? So here's the deal. Now we've got to go and look at this velocity vector. Now we're going to be pointed at some angle, right? So 3.5 meters per second is going to be pointed at some angle. There's going to be a cross component and an upstream component. what does this upstream component have to be so that it's 0?
Then 1.2.
Yeah, 1.2 upstream, right? So this side of the triangle is 1.2, yes?
Yes.
This is a key concept. Key concept, right? So if you want to go straight across, make that upstream component equal to the current. Yeah? Now, how do I find this side and how do I find that angle? This is C, this is B, this is A. How do I find A? How do I find theta? You could find theta and use a trig function. Or can't you find A without using sine or cosine? Like Pythagorean theorem, right? So A is going to be square root of 3.5 squared minus 1.2 squared, right? I'm using the Pythagorean theorem. Okay, that's 3.29. I'll go 288. 3.288 meters per second. So that's that one. Isn't this our velocity here, 3.288? Right, so this guy is this horizontal one. That's the only velocity in town. Okay? And then how do I find that angle? Well, now that we know this side, we could use any trig function. But what's the one that doesn't need to use A? Sine, yeah, inverse sine, right? Because sine, it's SOHCAHTOA, right? So sine is opposite over hypotenuse. So it's going to be this angle here is inverse sine of 1.2 over 3.5, which is close to the inverse tangent of 1.2 over 3.5, but not the same. So second sine 1.2 divided by, it's actually 20.05 degrees. Okay? Now, can we figure out the time to cross? Yeah. It's only moving straight across. Its velocity upstream or downstream is 0. That's the only motion it's got, right? And so the time is going to be this divided by this. So 120 divided by 3.288. Yeah, 36.5 seconds. You can probably move that time across, but it doesn't have anything to do on this side. It's like, gets over there and it's like, yeah? Can't do anything. Because, yeah, I mean, we already knew the answer there, right? Okay. So, yeah. So we get across a little bit faster than the other angle because it's more efficient. What is the velocity of the boat as seen from above? If you're in a helicopter and you saw this boat crossing the river, what would you see it do? Yeah, it moves across. It's got a velocity across, but not at all upstream or downstream. It moves straight across, and as it crosses this river, let's draw the river, okay? As it crosses the river, it's at an angle of 20 degrees, and it just goes like this. Yeah? It's pointed that way, yeah? But it's just moving straight across, just like you saw with the little cart thing, yeah?
Mr. Murray,
Yeah.
would it be faster to go straight, or to do like back, or just go straight across and then climb back up?
Oh, I don't know. Which is, strategically better. But, as far as shortest amount of time, point yourself straight across. Now, when you guys go to the airport, those little people movers, yeah? It's fun. You walk with the current. That's fun, right? You ever walk against the current? Yeah, I do that a lot. Okay? I'm sort of afraid of doing weird things at the airport because I might get arrested. The other thing you could do, and this is, people really don't expect you to do this, is if the conveyor belt is going this way, walk across the conveyor belt. Yeah. Does the motion of the conveyor belt affect my time in crossing it? No, not really. Does it affect people the way they regard me in the airport?
Yep.
Yeah. They think I'm crazy, but I'm not.